Everybody, can everybody hear me properly? I'm trying to use the tablet today. Let's see if I can write on the slides.
Yes, yes. The
Okay,
sound is very
great.
good.
Okay, great. Okay. So last time we were starting to introduce some important concept on control, specifically some classes of dynamical system, first order and second order, and their typical responses, time responses to, for example, a step input, and the relevant parameters associated to that. We will. I noticed that some slides were wrongly placed, so you will see them again, especially the slides related to the value of the settling time for a first order and second order system. So an important specification that we face. So now that we introduce what the model is, and we can start to think about designing a controller for a model of the system that we have at hand. And to design a controller, we have some specification to define. And the first one is that we want our controller to stabilize our system, because our system could be, for example, an inverted pendulum, or could be a mass that is unstable by itself, and it might need to be stabilized. This means that the controlled system must be able to don't diverge in face of changes of the reference, and also in face of external disturbances. And if after an initial phase that we call transient phase, the system should, a stable system, we saw that should arrive to an equilibrium point. And we see on the left the, for example, response to a change in the reference, that is the red line, and in blue the a response of the same system to a disturbance that is happening in the middle of the evolution of the system. And we saw that disturbance is nothing else than another input like a reference, but is an input that we don't decide usually. It's coming from the external. When we analyze the response, we see that there are two kinds of responses, the transient and the steady state. Yeah. This is the transient phase, that is when the system evolves and moves around from a previous equilibrium point to another equilibrium point that is relative to the new input that we give to the system. And the steady state is the equilibrium point where the system goes and stays forever if there are no external disturbances. And to design a controller, we need to consider some characteristics responses to some canonical input signals. And usually we saw already, we use the step input, or could be even the ramp and the sine input. And to define specification for the controller, we can define the specification at the dynamic level. So these are specifications that are defined on a transient response, or at the static level, that are performance specifications that could be defined to improve the steady state response. And so this static dynamic specification can be defined both in the time domain or in the frequency domain. And if we look at the time domain specification, we look at our response with the transient and steady state, and The static specification are mainly related to the steady state tracking error, which is the distance between the so it's the distance between the evolution of the output, that the equilibrium point of the output, and the reference. So how far away we are from the reference once we are in steady state. While the dynamic specifications are the rise time, that is the time that output needs to go from 10% to 90% of the final value. So this is the rise time. Then we have the settling time. This is the most interesting for us, and is the time that the output takes to get up to 5% away from the reference. Actually, if there is no tracking error, the reference will be the same as the equilibrium point, and so 5% from the equilibrium point or the reference. And the maximum overshoot, it's the maximum deviation of the output from the equilibrium point. And normally the overshoot is expressed in percentage, like 20% or similar. And the overshoot peak is the time at which, from the initial of the step input, because we are considering in this case is a step input response, the time that it takes to get to the maximum point, that is the overshoot point. And setting some dynamic specification usually means to set some upper bounds on overshoot. We don't want the system oscillates too much. And on settling time, we want the system to respond quite quickly or sufficiently quickly for our application. And these cases should be guaranteed in the worst case scenario. So we want to achieve a certain level of robustness, so we will see in face of disturbances, such that the settling time is at least a certain value. So for the system we saw till now, we have a nice expression to compute the settling time, that is 4 divided by tau, for a first order system where tau is the location of the is the time constant of the pole of the first order system, and for a second order system is 4 divided by z omega n, where z is the damping ratio and omega n is natural frequency of our second order system.
For the first order system, isn't 4 dot tau instead of divided?
Yeah, sorry, it was a mistake. Yes, good. Let's see if I can modify. No. Okay, I cannot modify right now, even though I specified that I want to modify, but I will remember. Yeah, sorry, it was a mistake. And in terms of overshoot, we have this expression that is an exponential and is related to the damping ratio. So bigger the damping ratio, the smaller the overshoot, and the lower the damping ratio, the overshoot is bigger, and the peak time. And if we want to go for dynamics and static specifications in the frequency domain, we should look at what we call the baud diagram of the system. And the plot diagram represents, sorry, I'm trying to hide, okay. I would like to see only myself here. Okay. So the plot diagram represents the frequency response of the system and is composed usually by two plots, one for magnitude and the other one for phase. We only see here the one for magnitude, and these plots usually are defined in a logarithmic scale. Why we want to use a logarithmic scale? Because if we have a big range of frequency, if you have a big range of frequency, with a logarithmic scale allows us to don't lose the details on the small on the low frequencies, and it allows us to compress, for example, the high frequency, and so have a big frequency range in a better detail. And usually so this kind of plots, they magnify the low frequency and compress the high frequency, and they are expressed in decibel unit that are relative unit of measurement. A decibel used to usually to express a power of or an amplitude in a logarithmic scale. You know that logarithm convert multiplication and division calculation into simple addition and subtraction operations, and also the operation of power. They are transformed into a multiplication. And if we look at the static specification in the frequency domain that is interesting for us, we think we have to look at the DC gain, which is the gain the system has at zero frequency, and is the relationship between the input and the equilibrium, and determines the steady state behavior. While the at the dynamic level, we have the closed loop bandwidth, or the bandwidth, that is the frequency range where the frequency response, now I write closed loop, but could be even an open loop system, where the amplitude of our frequency response is bigger than minus 3 dB. So this is the bandwidth of this system. And okay, I have a huge delay in the pen. Okay. And the maximum frequency of the bandwidth is called the cutoff frequency, and represents the maximum, the highest frequency of a sinusoidal input that can be tracked with an attenuation of 1 over square root of 2. Let's see. So this means that if we are trying to track our system it seems that the PowerPoint crashed. I will restart.
Anche la webcam si è bloccata. Ah no, ora è tornata.
I think PowerPoint crash. It doesn't like my pen. I think I will take a mouse. That's it. Okay, we're almost there. Can you see the screen?
Sì, ma potrebbe mettere in schermo intero?
No, no, ok. Ok. Sorry about that. I think the computer, oh, it crashed again. Maybe the tablet is not powerful enough to deal with this. Or maybe my slides are too heavy. Okay. So we want to show that minus 3 dB correspond to an attenuation of 1 over square root of 2. And actually, an amplitude in dB is equivalent to an amplitude, a decimal, 20 log to the in the base of 10 of the amplitude in number. And so if we know that multiplication becomes a power in logarithm, we can put transform this way. And then we want to know, because the logarithm is the exponent to give to the base that is 10 to achieve the argument. So we want to do 10 to the power of minus 3 dB equal to the argument. And then we see if we do the square, no, the square root, the root of 20th root of this, we obtain 0.0707, that is 1 over square root of 2. So minus 3 dB, it means an attenuation of amplitude of 1 over square root of 2. And for bigger frequency than the bandwidth, than the cutoff frequency one, so out of the bandwidth, we have an attenuation that is usually of a bigger factor than minus 3 dB. So you can go minus 40 dB, minus 50 dB, so we have a bigger attenuation. And the first goal of the controller is to stabilize the system, and also to artificially speed up the dominant dynamics. So to increase the bandwidth of our system. Let's say our system is stable and it's as a small bandwidth, and with the controller we can make it more reactive. So I think, for example, to a controller, a system of second order like this, and these are the poles. In this case, they are real poles that are located at 10 rad per second, the dominant one, and the higher frequency one at a higher frequency, because we saw that the far away from the imaginary axis, the higher the frequency. And with the controller, we can move the open loop poles in different locations, for example, here. So you see here that the dominant pole that represent it's actually what determines the bandwidth of our system. It's moved at higher frequency. So the closed loop bandwidth, for example, is doubling in this situation. Having a large bandwidth, however, is not always very good, because as the same reference is better tracked also at higher frequencies, also the disturbance that is usually at high frequency are less filtered, because they are reflected to the output in a similar way as the reference input does. So increase the bandwidth will also introduce more amplification of the, or less attenuation of the high frequency disturbances that usually are detrimental for the control system performance. However, in general, we want always to have a large bandwidth such that we can reproduce, we can track the reference input signal in a big range of frequency. Here I will present you some very quickly some block diagram algebra that are useful to compute your transfer functions whenever you assemble blocks like controller and the transfer function of your plant, and whenever you have a connection in series of two blocks, the equivalent transfer function is the multiplication of the two blocks. And in parallel connections with a summation point, you have the two transfer functions are summed. And this is very important. This is the feedback connection. So it's negative feedback, which what we want to use, or a positive feedback that we don't use. And this is the forward path transfer function. This is the feedback path transfer function that till now we saw it was 1, but if we have, for example, the sensor model transfer function, it goes here and is no longer 1. And in this case, the equivalent transfer function of this arrangement is G, so the forward path from input to output. Let's think this is the input and this is the output. So the equivalent block of this arrangement is the forward path transfer function G divided by 1 plus in case of the minus feedback, or minus in case of the positive feedback, HG. And if you want to shift the summing block, the sum point after a block, then you just replicate the block upstream, the two inputs, or shifting the sum point before the block, you need to, in essence, for the input that didn't have the block, you divide by 1/g. And using these tricks, you are able to really work out transfer functions for any complexity, because you reduce the loops and you're able to obtain with these rules a single transfer function from all the subcomponents. And I will provide you some in the slides a site that tells you all the composition rule for block diagrams. Now, an important thing that we always will be talking about, and is related to the phase delay I was telling you earlier, is that we can analyze, we can tell something on the stability of the closed loop system just analyzing the open loop one. So let's consider a feedback system like this, where we have in this transfer function LDS, LFS, both the controller and the plant multiplied. And this is equivalent to F. Yes, that is the closed loop transfer function, while LDS we call open loop transfer functions. And if we have this assumption that we don't have poles, positive real part poles in the system, so the system and the controller, both the system and the controller are stable by themselves, and we know that the Bode diagram of the amplitude of the open loop transfer function LDS is cutting the frequency axis only in one point, so it's not doing strange things like this. And we know that the DC gain, so it's cutting one point, and we call this point a cut frequency, where the transfer function LDS crosses the 0 dB axis. And 0 dB, you know, 10 to the power of 0, it's 1, and is the it's a unity amplitude, unitary amplitude. So where the modulo of our frequency response as unitary value. This is the definition of a cutoff frequency. And in correspond, we also want a DC gain, so the zero frequency gain positive. And if in this case we call the phase of phi c, the phase of the LDS transfer function at omega c, at the cutoff frequency, and we call the phase margin the difference between this 180 degrees and this phase at the cutoff frequency, we can define have a very nice criterion, which is the Bode criterion, that comes from a way more complex criterion that is the Nyquist criterion, that holds only this assumption that we almost always have satisfied in robotics and for robotic systems. So we can use Bode criterion, and tells us that the closed loop transfer function is asymptotically stable if the phase margin of the open loop transfer function is bigger than 0. This means if the phase at the cutoff frequency, it's bigger than -80 degrees. So if the phase delay that we have between input and output in our open loop transfer function is below under 80 degrees, we don't have. If you have more delays, then automatically you can say that this system, closed loop system, will be unstable. It's not possible to stabilize. However, if we have a bigger phase margin, so if you are more far away from the -180 degrees phase delay at the cutoff frequency, then we have robustness. So we can deal with bigger disturbances, and the system will remain stable. And also delays, because we say that the phase margin, in essence, it can be considered that is the amount of lag, the maximum amount of lag that the closed loop system can tolerate before becoming unstable. So if we add some delay to the system, we have our system in closed loop, we add some delays, and this delay usually in Laplace is expressed as an exponential, negative exponential of s times t, where t is the delay in seconds. And this delay that could be, for example, in your communication line or in your actuators, it affects the phase, reducing the phase, so eroding, reducing the phase margin. So the phase becomes more negative and gets closer to -80. And this makes such that the phase of LDS, or in this case of the open loop transfer function, becomes closer to -180 and closer to instability. And however, the delays itself, it doesn't affect the magnitude of the transfer function. Was clear till now? You have any question? Okay, then we can see how we can design a controller based on the concept of transfer functions. Let's start with a very simple controller. We will see this is a proportional controller. So we assume this controller structure. We have the reference position. Let's say we have our system is like a spring damper system. We want to control the position of our spring damper system to track a reference value. And to do that, we have an actuator that apply a force. And this force is proportional to the tracking error between the desired and the actual position. This is the transfer function of the controller, C of S, and it's simply Kp. Because it's the output of the controller, that is the control action, the force, divided by the input to the controller, that is the tracking error. And the plant dynamics we saw yesterday is this one. In Laplace, we can compute the transfer function dividing the output by the input, and we get something like this. That is a second order system. And if we compute the open loop dynamics, we multiply whatever is in the forward path, that is the controller times the system, and we get something like this. Then to compute the closed loop dynamics, we apply the rules we just learned on the feedback. So we added the feedback, and we know that is the forward plus divided by 1 plus, because we're using a negative feedback, the transfer function on the feedback line, that is 1 times again the transfer function on the forward path. And if you do the computation, you get something like this. And this is the characteristic polynomial. The parameter of our system is 5 kilogram mass, a damping of 200, and a stiffness of 100. And we want the question, the assignment that we have is that we want to select our controller parameter Kp to have both the poles, this is the first requirement, so coincident, at a frequency of -30 rads per second. By -30 because we have we want them to be stable, so we want the poles to be negative real part. The poles are the roots of the polynomial. We compute the roots of this polynomial, and we see that to have coincident roots, we saw this yesterday, the argument should be of this square root should be 0, and this is happening for a value of kp 1900. We are able to set whatever value for kp, so we are okay with the first requirement. But then the poles are, since this is 0, will be minus d over 2m, and in this case the value we get doesn't depend on our kp, so is fixed to minus 20 rad per second, and we are not able to satisfy the second requirement. So we see here an important result that with this controller we can satisfy only one requirement. And we will see that this is because controller has one parameter, so we are able to define only one criterion to be satisfied. And if we want to do more, we should use a higher order controller with a bigger number of parameters. Now, let's see the design of a controller from another perspective, another point of view that you might find out and willing to use. Let's say somebody gave you the transfer function, you use the transfer function method, otherwise somebody gives you the dynamic of your system in a state space form, and then I will teach you how to do the design of a controller and check the stability in this case. So let's consider a very simple model of a point mass sliding on a plane with friction B, viscous friction only B. You know, this viscous friction is creating a friction torque opposing the motion. We have acceleration of a mass times the mass equal to the input force. And in the state space form, we have the states of the system. Do you remember? We have two states, one for position and one for velocity, one input. And if you compute the state space equation as we did yesterday, we have the derivative of the position, which is the velocity. We set a 1 at the matrix in correspondence of the state of the velocity state, and then we have the acceleration with the friction part here, and the input force with the input matrix B here. And we using the same controller as the previous example, with this equation, we can find how this controller is expressed in the state space. So since our controller is only on the position, then we do a selection matrix that multiplies the gain Kp only for the state of the position, and for the velocity one we put a 0, and this comes with a minus, plus we have the reference that is multiplied this way. And if we put this u into the state space equation, we have x dot equal to ax plus b. We replace this u as minus kx, this part, and b kp xd, x desired, this part. And we see that this term is also dependent on the state, so we can put together with the other one, and we have a new input here that is to the system, that is the reference. And so the closed loop system is just a system that has a new input that is a reference to track, and a new state transition matrix that is being changed thanks to the action of the controller. And to know the stability of this closed loop system, in state space form, we know that we need to check the location of the eigenvalues of the prime values of the matrix A minus BK. And to compute that, let's do that. So we take the A matrix, it was this one, the B matrix, and the K. And if you perform the computation, sorry, here there is a term missing. There is a B over M. And computing the eigenvalues of this matrix, it means compute the root of that determinant of Si minus A bar matrix, which is this matrix here, and set it to 0. So if you compute the determinant, we get a second order system, sorry, a second order polynomial, and the root of this polynomial will be the eigenvalues. We can see that Kp affects omega n here. You remember the second order system Laplace transform, but because omega n is also here, Kp affects also the damping. And if we compute the roots, we have this expression, and according to the sign of this argument, we have, if it is negative, we have complex roots, and if they are complex, the real part is only this one. And if they are not complex, which means that the argument is positive, then we have real roots. And in the case of real roots, we have this value plus something that is the same number, but reduced by some quantity. So whatever it comes out, it's a number that is smaller than B over 2m. So whenever we have the negative root that it's summing the negatively this number, we have a negative root. But whenever we sum it positively, we sum something that is smaller than B over 2m. And so we will still have a negative number. And this means that both situations, for any value of Kp, we have roots or eigenvalues always with negative real part, and it means that for every value of Kp, the system is always stable. If we do the same thing, the same controller for a discrete time system, so a discretized version of the system we have, we will see that this is not true, and the system can become unstable for big values of Kp. So even if in a continuous time your controller is stable, be aware that whenever you implement for the discretized version of the system, that the one you have when you're sampling your system, your sensors, so you can be unstable. In general, whenever you increase Kp a lot, the system become unstable. Okay, everything is clear till now. Please close. I think this PowerPoint presentation was quite big to digest for my tablet. Now we go to the next batch of slides that is talking about PID. Okay. These slides will talk about P control, proportional control, an improved version with proportional derivative control. What happens whenever you add some feed-forward action, and the PID control with the integral action as well, and some anti-wind-up techniques that are important whenever you have an integral action and you have some saturation in your actuators. So why we care about PID controllers? Because in the industry, these kind of controllers that are called fixed structure controller, because a fixed number of parameters, maximum 3 in the case of PID, are the mostly used. And the good thing is that these parameters can be tuned quite easily to get desired performances. And the most famous fixed structure controller is the PID, which stands for proportional integral derivative, and it's very simple and effective and very diffuse because of the simplicity. And to define a controller, a PID controller on a system, we can try to use our model of our actuated link, where we have a DC motor driving a single link, and we want to design a controller for this plant. And we quickly recall the model of the plant, the Kirchhoff law on the electrical part, the parameters, the resistance of the coil, inductance of the coil, the torque and velocity constant, and the mechanical domain, the Newton equation on the shaft of the motor with the rotor inertia and the viscous friction at the shaft. And we saw that the transfer function, the block diagram of this system, it was this one, and where we usually neglect the electrical dynamics by setting the inductance to 0. So from this block diagram, using the rules that I told you before, the block composition rules, you can by yourself see and be convinced that this is the transfer function between input and output, because we have feedback part here. So we have the forward part divided by 1 plus the feedback part times the forward part, and this ends up to be this, because both denominator of the forward part and at the denominator level they cancel out, and everything is in series with 1 over s, which is the integrator that integrates the velocity, the angular velocity to angular position. And so we have a multiplication for the 1 over s. So this is the transfer function of our system. We want to first introduce a proportional control, a P controller that is the same controller we saw in the previous example, and is a control action because our controller, its output is doing a voltage control, so its output is a voltage, and the control action is proportional to the tracking error. So we close the loop. We want to do position control. So we close the loop on position. We have the desired position. We compute the tracking error, and we multiply by Kp. We get the voltage, and we apply this voltage to our plant that is composed of the electrical motor actuator, where we neglect the electrical dynamics, and our load. And the closed loop transfer function, you apply the same rule we explained before, and we get this expression, where we see that the controller parameter is here and here. And because the denominator of the transfer function is a polynomial of the second order, the system is a second order system, the closed loop system. And we see that the feedback, since the dynamics is dependent only on the denominator, only the characteristic polynomial, and the Kp is present on the denominator, we see that the feedback changes the dynamic of the system. So not only ensuring stability, but also changing the dynamics. And we can say, we saw before that a P controller is always asymptotically stable for positive Kp, values of Kp. Of course, I didn't say before, but Kp should be positive. I will correct this in the slides. This is true only for a second order systems, because for a higher order system, you will see that there is that can be a phase delay. There can be a phase delay increase, and this delay can go beyond under 80 minus 180 degrees. So in case of higher order system, the system can become unstable. We have just one design control design parameter, Kp, and because we have only one parameter, we saw that the two poles cannot be independently assigned. In this case, since we are talking about a second order system, the natural frequency and the damping ratio of the complex pole pair, for example, in case there are complex roots, they are coupled, and increasing the Kp, it speeds up the response, and this means increase the bandwidth in general. However, the transient response or the disturbance rejection capability might not be satisfactory. And as I said, for higher order system, more than 2 second order, increasing Kp may lead to system instability, and you need to do a proper analysis for that. While if we introduce an additional term to the controller that is dependent on the derivative of the tracking error, we get a proportional derivative control. So our voltage, sorry, this is a dot. Again, we neglect the electrical dynamics, and if replace, this time we rather than using the transfer function approach, we directly, I will show another way of doing that, of analyzing the dynamics, and we replace this control law directly in the dynamics of the system, in the differential equations. Since we have neglected the electrical dynamics, we just have a mapping, a pure scalar mapping between the torque and the voltage. And if we replace this definition of the derivative of the tracking error, which is the desired position minus the desired acceleration in case of the second derivative, minus the acceleration, and desired velocity minus the actual velocity, we can obtain an expression like this. And if we want to, we will see here we don't have any we have only the actual value, so we should replace it with theta dot desired minus e dot, and the same for the velocity, we replace with theta dot desired minus e dot. And if we further develop this, we see that putting everything on the left, we get the tracking error dynamics, while on the right, we have our something dependent on our input, reference input. In particular, we have a second order system, and that is not converging to zero for time varying references. So if our reference is constant, like a step input, then its derivative and first and second order derivative will be zero, and the convergence, the error will converge to zero. But if, for example, a sinusoid, which is changing over time, this is not going to happen. And in a PD gain, in a PD controller, we can set the KP and KD gain and tune them to completely shape the transient behavior of the second order system. This means that since we are talking about a second order system, we are able to both set the natural frequency and the damping and improve the response of the error dynamics, increasing, for example, the speed of convergence and regulate the overshoot. So satisfying some dynamic specification. For example, in the overshoot, to have a certain overshoot, we will have a certain value of damping and angular natural frequency. And so you can say that you can translate your user specification that might ask you, I don't want more than 20% overshoot, into something that can be converted in numerical values for the gains of your controller. So, for example, setting the damping, you have different responses from the underdamped case to the overdamped case. And this is the expression that from the previous equation we can obtain for the damping ratio. And this was the, if you remember the analysis we did for a second order system, the natural frequency. We see that the KD and KP parameters are affecting both of them. And in particular, KP directly affects omega n, but also Z. And to increase the damping, we should decrease KP, making the denominator smaller, or either increase KD. While to reduce the damping, so make the system more oscillatory, we need to increase KP, which is kind of making the system stiffer, and reduce the damping, so less damping of the oscillation. And if we set the damping to zero, we have that the overshoot peak is maximum, but in general, we cannot never obtain this situation, because even if we set KD to zero, because of, what is this? Because of the viscous friction, because of the passive friction in the system. So as a thumb rule in your design, I suggest you to set your damping ratio to bigger than 0.7 and the natural frequency under the resonance of a mechanical structure. Because if you go at the resonance of the mechanical structure to move, then you will excite unwanted vibrations. Everything is clear? Okay. Then how can we further improve tracking? We saw that we cannot track time varying reference. So what about that? How can we improve? And a way to improve a PD control, for example, is to provide additionally to the PD control action, that is a feedback action, adding a feed forward action. So a term that we compute in a certain way, based on some model of our system, that will relieve the effort of a control action in tracking the reference. So what can we do, for example, as an idea? We can provide already, if we know how the, can you see this? This is not slowing down my system. Okay. So to achieve the desired acceleration, we can already provide the voltage necessary to achieve that acceleration and also compensate for friction. So if we have the desired acceleration, desired velocity, we can pre-compute the friction torques and compute the voltage to compensate for these friction torques. In addition to the feedback of the PD control. And so this is a feed forward term that is added. And if we look at the closed loop dynamics, this time you see that the reference derivative are there, and also the first and second derivative. And if you compute the aerodynamics, this time we won't have problems, because the aerodynamics, the input to the aerodynamics will be at 0. So the aerodynamics will converge into 0, will naturally converge to 0. And this means that the feed forward term relieves the work of the feedback controller, improving the tracking, but is kind of sensitive, can be sensitive, for example, to model inaccuracy. For example, if the inertia of our motor is not known properly, it's misestimated, or even the friction has an error of 20%, then we will have a wrong cancellation of, not a cancellation, we will have still some residual terms here that prevents the tracking error to be 0. And we see here on the left plot for a sinusoidal reference that in case of no feed-forward action, we always have a kind of delay in the control action. And with feed-forward, even if we start from an initial tracking error, let's say the reference is different from the actual initial state, from the initial state, then after a while the feedback action will bring the tracking error to be 0, and because of the feed-forward term, the tracking will be perfect. However, if you have a wrong estimation of the inertia of the motor, for example, you think the inertia is bigger, you provide more voltage than is needed, and you can have overshoots, or you might have bad tracking as well. So be careful with the feed-forward action, and be sure you have a proper model for that. So we can do the break here, if you're okay, and we come back in 15 minutes. Okay. Let's start again. Are you there?
Yes.
Okay, good. Somebody's still alive. So the next structure that we see, it's the PID controller, that it's nothing else that adding also an integral control action. And the reason for which we usually add integral to control action is to achieve zero error at steady state. For example, constant disturbances, like for example, a gravity or a constant offset. And this control action, to be able to set the steady state error to zero, should be in the path before the entry point of a disturbance. And usually, since the controller is before the transfer function of the system, then this is always the case. And the control law that we set at our voltage to achieve the PID controller is this one. We have a proportional part, a derivative part, and we have something that is dependent on the integral of the tracking error. And we multiply for the Ki gain, which is the integral gain. And this is in the plus domain is seen as this. Derivative becomes S, and the integrals becomes 1 over S. So we have this term here. And if we compute the closed loop transfer function using the rules that I told you previously, you get something more complex. In particular, you can see that we have the KD, KP, and KI gain both in the numerator and at the denominator, and you can see what is the order of this system. Now that you know what the order is. What is the order of the closed loop system? You know, the order is the order of the characteristic polynomial, which is third order. So maximum power is 3. So we have a third order system here. And to check stability, in this case, I suggest you to use, there is a criterion that tells you what are the roots of a polynomial, whatever order polynomial, checking some parameters. For example, can tell you that to have negative roots, you should have a certain relationship between the parameters of the polynomial. I won't go into detail for this. You can find, if you need some information everywhere on this criterion. But the important thing is that this system as negative real part poles for if the proportional gain is always positive, the derivative gain is always positive, and if the integral gain is in this range. Out of this range, one of the root becomes positive and the system becomes stable. So you start to see here that as the controller complexity increases, you cannot do whatever you want, and you start to have some constraints between the parameters themselves of the controller. we said it's no longer a second order system, so we cannot use just natural frequency and damping to place the poles, and we need to use a pole placement technique to locate the poles wherever we want, and to therefore to shape the transient. And these pole placement technique are usually implemented with a function place in MATLAB quite easily. Finally, just this is a repetition of what we said. If we want to do current control, and a measure of the current is available, so we no longer have a control. We no longer have a controller that outputs a voltage, but we want to, for example, to have a controller that, in the case we want to control the position, outputs a desired current, and then another controller, which is an inner loop current control, provides the voltage to track this desired current. And since the electrical dynamics is quite fast, we compare with the mechanical one, it's usual to design the current controller to achieve a very high bandwidth, like thousands of hertz. And in the design of the current controller, you can see the back EMF as a slowly varying disturbance, because it's depending on the mechanical dynamics, that the shaft angular velocity, which is quite slow. It's certainly not 2000 hertz, and the current controller will effectively reject this influence of the back EMF. And this is, as I said, I introduced a slide in the previous lecture on the controlIntro about cascade loop approach, where we have one current loop inside inner loop that can be seen as instantaneous from the external position or speed controller. So we achieve like instantaneously the desired current tracking. And therefore, in this course, we will assume that the motor torque is the control variable for our position speed control problems. And be sure that you always update, download the latest slide, because I am continuously finding typos and doing correction and improving them. So just to be sure, you always can download the latest version. And some other things that we saw that are important in a control system is to consider non-idealities in the actuation system, in the sensor system, and these non-idealities we saw that can affect the control performances. In particular, there are actuation saturation, so the actuator variable cannot be increasing indefinitely. It will reach a point in which there is a maximum voltage, for example, or a maximum current. We saw that we can have backlash that can be modeled as hysteresis, Coulomb static friction, and sensor quantization. And finally, this digitalization of the controller that we saw can introduce phase delay and instabilities, and we reduce the maximum values that we can set to the gains of our controller. So it sets a bound on the maximum values that we can set. And so whenever you design the controller on the system without all these non-idealities, it is important, it is good to test it with improving the simulation, make it more realistic, adding this phenomena, and see how the controller is still behaving, if it's still behaving good or bad. And this is an example, Simulink example where of these non-idealities, you will have something very similar in your lab with the saturations, with the friction, hysteresis, and quantization is not here, but we will also have that. And one thing you could try as well is to consider that you have uncertainties on your nominal parameters, for example, on the inertia, on the friction. And you can play around trying to change the inertia, for example, of 20% and see if still the controller behaves in a proper way. Everything is clear? Okay, then an important issue that you might have whenever you have an integral term that you will certainly have whenever an integral term and actuation with saturation is the problem of wind up. We said that the integral term of the PID that we are adding, it's increasing over time. So the integral wind up refers to the situation where the integral continues to grow indefinitely. And this usually occurs when the controller outputs reaches the saturation. That is a situation where the controller output, the controller variable can no longer affect the controlled variable. So the controller output, which is the control variable, has no longer influence on the controlled variable. For example, the position of our motor. And because of this physical limitation, the input is saturated to the maximum value, for example, of the voltage we can apply, or the minimum value of the voltage. And these bounds could be different, while inside, if the control variable is inside the maximum and minimum values, it's appropriately applied to the system. Whenever it gets outside, lower than the minimum bounds, it's saturated to the minimum bound, and greater than the higher bound, then it's saturated to the higher bound. And this saturation block, it's drawn like this way. And we see that here the saturated control variable is different, can be different from the control variable. And whenever there is a saturation, what happens is that the controller input does not depend anymore on the error. There is a cut in the loop, and the system starts to evolve in open loop. And if the tracking error maintains the same sign for a certain time, the integrator part of the PID increases its value, and while the saturation still remains at the same. So the input to the system remains the same. So the problem is that we have this wind up, and whenever the tracking error changes sign, because for example, the output has reached the reference and but still starts to grow, the error changes sign, and the control variable U starts to decrease, but still needs to discharge completely before entering into the linear region that is inside the saturation, out of the saturation, and starting to modify the input to the system. And In this time interval, the PID cannot control the evolution of the output, and we can have very large overshoot or oscillations. So you have this charge and discharge before getting inside the saturation of the integral action. And to avoid this effect of wind up, is necessary that whenever the actuator saturates, the integration of the tracking error stops, and the value of the control action remains at the maximum UH, for example. In this way, whenever the error comes back to zero and starts to become negative, let's say, because the output reached the reference and went beyond, then the actuator it's immediately coming back into the linear region. And the technique there are many techniques. In my opinion, this is the simplest one, and is the one that compares the actual input and the commanded input, the saturated input. And if they are the same, the saturation is not active. Otherwise, we reduce the integral error, but their difference. So this difference that is usually happening whenever the integral is going beyond the saturation becomes a negative number that decreases the tracking error and stops the integration, removes stops integrating the control action. So this is the scheme you should use. You have the saturation of U here minus the U variable, then you multiply by a gain that tells you how fast you want this to react, and then this is added to the E tracking error, and this is then integrated and summed up to the other part of the PD controller. So this is a PID controller with anti-wind up technique. Is everything clear?
I have a question.
Yeah.
Regarding the transfer function of the PID,
Yes.
if we put everything together, we have that the degree of the numerator is greater than the degree of the denominator.
Next slide.
It is feasible to build something like that, or?
Yeah. The next set of slides will be dealing with that problem. Good question. It's as it is, the PID is not realizable because we have something dependent on a future. It's not causal. It's an improper transfer function. We will see in the next slides, in the next batch of slides, this. To finalize, I show you some simulation with the actuation saturation, and when there is no saturation, the anti-wind up doesn't have any effect. When there is a saturation, we're sure that with anti-wind up, the controller output you change as soon as the error change sign, avoiding the integral wind up. And we see here a situation without anti-wind up. We have a very big oscillation, and we see that the controller output U, it's charging and discharging, and while the saturated one is cutted here. While in the anti-wind up technique, we see that both are the same and they are properly clamped at the saturation level, and the oscillations are much smaller. So to go for the next slides. that will discuss exactly about the topic Uros was raising as a possible issue. Okay. And this set of lectures is talking about the tuning. How do we tune a PID controller and implement, do a digital implementation and a realizable implementation as well. So we recall here the structure of our control system, the PID. We can have a disturbance, I didn't say, also on the measurement, that is usually called N, and a disturbance at the output of the system, a disturbance on the input of the system. And we might have some differences between the actuated input and the saturated input. Sorry, between the control low input and the actuated what we really actuate as control low, for example, in presence of a saturation. And we, whenever we write a PID, we can have two forms, two structures. This is the parallel form, and this is called the standard form. And you see that in the parallel form you have gains Ki and Kd, while in the standard form for the integral you relate the sorry, I'm trying to find the arrow. Okay. You relate the value of Ki to the value of the proportional, and you use Ti, that is the time constant of the integrator, and the same for the derivative. And this is the same thing in the Laplace domain, where Td is the derivative action time constant, and Ti is the integral action time constant. And if we want to do a qualitative analysis of the three components, we can say that in the case, for example, of a pure proportional controller, we have that the steady state error, you remember, this is the transfer function between the reference and the tracking error. And if we apply the final value theorem, that is computing the limit of S converging to 0 of S and the transfer function times the input, we can get something like this. And in this case, we see that if we increase the Kp, we can reduce the tracking error, but this will never become 0. And the proportional action is, in fact, consider how far the output is from the reference, and its contribution is only based on the tracking error at the time t. So the control action times t is only dependent on the tracking error at time t. And if the tracking error grows or shrinks, the influence of the proportional term immediately grows and shrinks proportionately. And the proportional action accelerates the transient, can be used to accelerate the transient and reduce the steady state error, but not setting to 0, because to set it to 0, the Kp should go to infinite. And if the controlled process has more than 2 poles, you remember each pole, you should remember that creates a phase delay of 90 degrees. So with 2 poles, you can have maximum phase delay of under 80. But so you are not, you're never unstable. But if you have more than 2 poles, you can have a bigger phase delay, go beyond the 180 degrees, minus 180 degrees, sorry, and become unstable, even with a simple proportional controller. And we said that accelerates the transient. This means that the proportional gain can increase the bandwidth at the price of this phase margin, which is the responsible of instability, the reduction of phase margin. If we talk about the integral action, the integral action considers how long the output has been far away from the reference. It guarantees 0 steady state error for a step input. In general, what happens is that the control action increases till the tracking error nullifies, and the influence of the integral term at the frequency level, let's say, it's that introduce a phase delay of 90 degrees, so minus 90 degrees. And therefore, increasing Ki can also increase the delay, and that leads to oscillations and possible instability and increase in the settling time. And if we compute the, sorry, there is a parenthesis here, the final value theorem for the tracking error, in this case with a PI, for example, controller with an integral actions, we see that if we set S to 0, we have this number over 0, and so we have infinite here, and this is the limit of this is 0. So the integral action has achieved 0 steady state error for a constant step input. Is not said that is if you use a ramp input or a different input, this is true. The derivative action instead consider how fast the error is changing at the current moment, and introduces a phase advance of 90 degrees. A phase advance, it means that we can recover some phase delay, and therefore the increasing KD parameter can improve stability. However, a derivative action amplifies high frequency noise. So to have a thumb rule summarizing table of what the three parameters do in terms of what matters to us, that are stability, steady state error, settling time, and overshoot, we can summarize it here. And you see here that increasing KP reduces the settling time because increases bandwidth, improves the steady state, the transient response, but also increase the overshoot, so decreases the stability, while the integral action nullifies the steady state error, and in general can decrease also the stability and increases the settling time because it takes more time to settle down, and also can increase overshoot, especially if you have a saturation, and that the action usually improves stability, and it's irrelevant for settling time. And because it's adding damping, the derivative action is also decreasing the overshoot. Is everything clear till here? So we arrived exactly to the question of Uros that was about the realizability of the PID. If we look at the transfer function, we get and we compute the numerator and denominator, we get 1 pole, sorry, at the origin, and 2 zeros to roots of the zeros. So a degree of the numerator is 2 and is bigger than the degree of the denominator, which is 1. This means that this transfer function is improper or not causal, non-causal. And it means that it's not physically realizable because it requires the knowledge of a signal in the future. And the problem, if you look at that, you would have, without this term, you would have the same degree of numerator and denominator if you have just the PI controller. So the problem is related to the derivative action that has some other issues. For example, if you have discontinuous reference change, you can have the derivative that spikes to infinite, and this is called derivative kick. And to bypass this issue and also make the system realizable, what people do is to filter the derivative contribution with a low-pass filter. And this means we saw that the first order filter is just adding a pole, and this pole we add at high frequency, because this way the attenuation effect of the pole will not affect the low frequency, the derivation at low frequency. Sorry, differentiations, this was wrongly written. And adding a pole at high frequency to the derivative term is doing like this. And usually this, the frequency of this pole, which is 1 over tau, as a time constant tau that is related to this rule. And for frequency below the cutoff frequency 1 over tau, the real PID behaves similarly to the ideal one. And you can see the bode plot of the PID controller. The ideal one is the blue one, and the one with the added pole, high frequency pole at the derivative is this one, and this pole is whatever makes this change of slope. And you see that before 1 Hertz, I'm not sure if these are Hertz, yes, before 1 Hertz, the two responses are, the two Bode diagrams are the same. In alternative, what people do is they differentiate only the output and not the error, so avoid the problem of discontinuities in the reference signal that creates spikes in the system. But you should also always add a high frequency pole for reliability. If we want to implement as we said before, previous lectures, controllers on a digital system, we need to consider that they need to consider the presence of AD converter and DA converter, and because we want a discrete formulation that has sample inputs from the sensor of this, so a sample error signal, and also we have a discrete so digital signal for the error and digital signal for the control law. And if we call TS the sampling time, we see that P action remains the same. It doesn't change from the control to the from the continuous world to the discrete world, while the integral action can be approximated considering the area under the sample, the sum of the area under the samples of the error, and While for the D action, ideally we should do the difference quotient, the rapporto incrementale in Italian, what we call rapporto incrementale. But to do the difference quotient, we should use the sample at, do the difference between the sample at k+1 minus the sample at k, and this is not possible because we'll be in the future, and so we do a backward differentiation, and we do the difference quotient between the sample at time k and the sample at time k minus 1. And putting everything together, we get the digital implementation of this PID. And we see here that we have derivative action, integral action, and proportional action. And we still have the same problem of we saw in the averaging filter, that you need to keep in memory all the samples to compute the integral. So similarly, what we did for the averaging filter, recursive implementation, we can define the integral term in velocity form, which means considering that every time a difference with respect to the previous sample. So if we consider the sample of the integral, the value of the integral time k, we have something like this, sum of all the errors, tracking errors, values, samples, times the sampling time, times ki, that is the integral gain. And we can express this looking at the fact that this one times ki ts is just the previous value of the integral. So we only add the actual value of we integrate only the last sample. Finally, we arrive to the point where we want to tune the parameters of this controller that we designed. And the tuning, in essence, we could do whatever we did, that is trying to locate the poles or do a pole placement method, or we can rely on some magic rules that have been found by Ziegler and Nichols, that conducted many experiments in this previous century, and propose some rules to determine the values of the parameters. And the rules are based on the standard form. That's why we introduced that, even if I don't like it much, and are to find the values Kp, Ti, and Td. And they're based on the transient step response of the plant that we want to control. And the method is called the method of Ziegler and Nichols. And it might apply to plant with complex conjugate poles, but also first order systems that have a response without overshoot. And this response should be characterized by two constants that we call delay time theta and time constant tau. And to determine this constant, we draw a tangent line at the inflection point of the curve. We will see in the next slide what this means. The process, of course, should be stable by itself, should not diverge. So we give a step input to the k delta u, to the, sorry, we give a step input to the system delta u, and the process, our plant will evolve, and we reach the equilibrium y infinite, which is equal to the DC gain times delta u, and where k is the static gain. And if we have a second or higher order behavior, we have something like this. We have a first order, we have something like this. And we want to simplify this system such that it's something like a delayed, we saw this is the delayed system transfer function and a first order system. And we can deduce the process parameter from this step response that we do at the beginning, drawing the tangent to the step response in the point of maximum slope that for a first order system is here and for a second order is here. And we get the intersect of this tangent with the x-axis and we compute the delay theta. And the second point, it's tau, is the time constant of this approximated first order system and can be computed from the T1, that is the intersection between the this tangent and the equilibrium point and from the theta. And the static gains, of course, is the ratio between the output equilibrium point and the magnitude of the step input. And using this theta, tau and theta and DC gain, we can set the parameter proportional, integral time constant and derivative time constant for our controller. So in case of a PID, for example, we want to use a PID, we set these values for the KP and these values for the TI and TD. And this will ensure that the response we will get from our system will have an overshoot about 25% and a good settling time. So try to do the best that you can. And this is a starting point then to do start a fine tuning of the controller using the basic rules that relate each parameter to the response characteristics that we defined before. So this is just a starting point to give some values to the system, to the parameter of the controller. Then you can start to tune them better. And let's think about, for example, we have this higher order system. This is 1, 2, 3, 4, fourth order system. And this system is asymptotically stable. It has 2 poles in -1, 1 pole in -0.5, and 1 pole in 2. And if you do the step response of this, you will have this behavior. You do the tangent, you compute theta. Theta is 1.46. Tau is around 3.3. And then you can approximate this second order, the fourth order system with the first order system with delay that has this shape. And using, then we said, well, let's try to see what we do, just tuning our PID by trial and error. We, for example, use a proportional. We set KP to 2, and we get a rise time of 3 seconds, steady state error, and large overshoot. And if we increase the KP gain, the oscillation becomes larger. If we use a PID controller, for example, after many trials, we come up with these settings, and we see that slight variations of these gains can lead to instability, and we still have large overshoot and very, very long settling time. So we need some help from Ziegler-Nichols to set a reasonable choice for these values, to then do the fine tuning, and using the approximation we did before and computing the Ziegler-Nichols from the Ziegler-Nichols table, the value of KP, TI, and TD, we get these values, and applying them, we see that we have this response is the overshoot is not really 25%, it's around 30, and but we have a good settling time of 16 seconds and less oscillations. And of course, zero steady state error because we are using an integral action. So this was the end of the control part. We are about to be over time, and so we finish this part this day, and next week we will discuss about we'll shortly introduce the lab, and we will go through the lab. At the beginning, we will give you some time to try out the lab exercises, and then me and Octavio will go through the solution of the exercises to show what are the results and discuss the plots and the results that we get for each exercise. Unless you don't have any question.
The lab will be on Monday.
Yes.
Okay, thanks.
Okay, so see you on Monday and have a nice evening.